Welcome to the deep dive. For decades there's been this really fundamental question floating around about existence itself.
Right.
It's captivated philosophers, physicists, I mean honestly, probably anyone who's ever seen The Matrix.
Absolutely.
The question is this reality, the one we're in right now, is it genuine? Or are we just, I don't know, code running on some massive cosmic hard drive?
That's the simulation hypothesis.
Yeah.
And it really jumped from sci-fi to, well, serious academic discussion, didn't it? Mostly thanks to Nick Bostrom's 2003 paper. It was pretty influential.
Hugely influential.
The idea was, well, kind of simple on the surface. If advanced civilizations can exist and if they get enough computing power, then just statistically, odds are we're probably living inside one of their simulations,
Yeah.
like a historical rerun or something.
Yeah, and the real frustration for 20 years now was, it felt like pure speculation, unfalsifiable.
Exactly. A cool thought experiment, maybe, but how could science ever test it?
Huh.
Why do you prove you're not living in an experiment?
You couldn't, but that seems to be changing now.
It really does. Our deep dive today is looking at what's being called a groundbreaking mathematical proof, one that claims to settle this question for good.
Settle it. Wow.
Yeah, the core claim, based on the sources you shared, is pretty stunning, actually. It says our reality is fundamentally real and, crucially, not computable.
Not computable. Okay, let's unpack that. So we're looking at materials about a research team. Sounds like they tried to fit the universe into a computational box and found it just didn't fit.
That's a good way to put it.
Okay, so the mission for you listening is to really get into the nuts and bolts here. We want to understand the specific arguments, both mathematical and physical, that this team used to apparently rule out the idea that the universe is a computer simulation.
So let's start with the team. The research lead was Dr. Mir Faisal at the University of British Columbia. But it wasn't just him, it was a collaboration. International physicists, mathematicians, a real collective effort.
And importantly, this wasn't just some paper dropped on a server somewhere, right? This went through peer review.
It did. Published October 2025. It appeared in the Journal of Holography Applications in Physics. And their big claim, the headline finding, is that the universe's fundamental nature is, and they say provably, non-algorithmic.
Non-algorithmic. That word again, let's clarify that because it sounds key. When we talk simulation, we're talking computers.
Always.
Right.
And all computers, no matter how complex, they run on what we could call a computational foundation. They execute algorithms, which are just, finite sequences of logical steps, predefined instructions.
Right. So the logic follows. If you want to simulate reality, the laws of physics themselves must be fully describable by algorithms. You need the complete rulebook written down as code.
If you can do that, then theoretically you could run the universe on a machine. That's the necessary condition.
Makes sense.
So the logical barrier they're proposing becomes pretty clear. If reality at its deepest level contains elements that are inherently non-computable, things that algorithms just cannot capture no matter what.
Then it doesn't matter how powerful your computer is.
Exactly. It's not about processing power or waiting for better tech. It becomes a matter of logical impossibility. No computer could ever simulate something that's fundamentally non-algorithmic. It just can't be done.
Okay, this is where, for me, it gets really interesting. Because the sources say the proof doesn't start with, looking through telescopes or smashing particles. It starts with pure math, foundational logic.
So that's the core of it. They argue that if physics were entirely algorithmic, it would immediately run headfirst into contradictions already proven to exist within formal mathematical systems. Fatal flaws.
Okay, lay it out for us. What are these mathematical pillars?
They rely on three really major theorems from 20th century logic. These basically establish the absolute limits of what any formal computable system can do.
Okay, let's take them one by one, because this seems critical. First up is Gödel's incompleteness theorem, 1931.
Right, Gödel. He proves something profound. Any consistent formal system that's complex enough to include basic arithmetic, well, it will always contain true statements that cannot be proven or disproven using the rules of that system itself.
So there are truths that are unreachable from within the system.
Exactly. There's an inherent incompleteness baked in. So
Yeah.
Translate that. If the universe were just a complex program, a closed system,
Then there would have to be physical truths about that universe that the universe's own laws, its own code, could never actually prove or derive.
precisely. The code would contain, let's say, internal inconsistencies or paradoxes. True things about the simulation that the simulation's physics couldn't account for logically. It can't be fully self-contained and consistent.
Okay. Pillar number 2, Tarski's undefinability theorem. This one's from 1933. Sounds a bit more abstract.
It deals with truth and self-reference. Tarski showed that the very concept of truth for a formal language cannot be fully defined within that same language.
Okay. How does that apply here? Like, a map can't contain a perfectly accurate map of itself, including the map?
That's a good analogy, yeah. Think of it like this. A simulated reality, its underlying code, could never generate a complete and formally true description of its own physics from within its own rules. It would always be incomplete or paradoxical when trying to define its own truth state.
So the simulation can't achieve total self-knowledge. Algorithmically speaking, it can't fully grasp its own nature using only its internal logic.
That's the essence. If reality is just a program, defining its ultimate truth or proving its own consistency from within becomes logically impossible because of these limits on self-reference.
Got it. Okay, and the third pillar, this one's more recent, Chaitin's complexity limits from the 1960s.
Right, Gregory Chaitin. He worked on algorithmic information theory. He established basically absolute limits on the complexity that algorithms can even describe.
Limits on description.
Yeah. He proved some information is algorithmically irreducible, meaning there's no shorter way to describe it than just writing the information itself out in full. Think about data compression.
Okay, like trying to zip a file that's already perfectly random. The compressed version isn't any smaller than the original.
Exactly, that kind of idea. If reality were simulated code, you might expect deep down to find some elegant compression. Simple rules generating all this complexity we see.
But Chaitin suggests some aspects of reality might be fundamentally complex, irreducible. You can't boil them down to a simpler algorithm.
That's the implication. The information content is just too high to be generated by a significantly smaller set of rules.
So wrapping those three up, Gödel, Tarski, Chaitin, the research team's conclusion is?
It's powerful, they argue. If the laws of physics were entirely computable, if you could write them down perfectly as one complete algorithmic system, that system would inevitably contradict these fundamental theorems of logic. It would be incomplete, unable to define its own truth or unable to capture irreducible complexity.
Therefore, physics cannot be fully algorithmic. The universe is too logically rich, too complex to be just a computer program.
That's the mathematical punchline.
That feels incredibly strong, like a purely logical refutation. Do the sources mention any pushback? Any potential loopholes in applying this math to physics?
The sources presented as quite robust. The only real way around these theorems would be if physics itself isn't based on consistent logic, which, well, that would basically undermine the entire scientific method.
Right, we kind of have to assume the universe is logically consistent to even study it.
We do. So Faisal's team took this mathematical impossibility and directly connected it to the structure of physical law at its most fundamental level.
Which brings us neatly into the physics side of things. Because this mathematical argument has huge implications for the search for, well, the Holy Grail, right? The theory of everything.
The TUE, yeah. That single framework trying to unify quantum mechanics and general relativity, what we often call quantum gravity, that's supposed to be the ultimate description of reality.
And this is where Faisal's team claims the really revolutionary physical finding, based on the math.
Correct. They state they mathematically proved that no fully consistent computational theory of quantum gravity can possibly exist.
Wait, hang on. See that again? No computational theory?
That's the claim. If you try to write down the ultimate theory of reality purely as an algorithm, as code, you will inevitably violate the logical constraints established by Gödel, Tarski, or Chaitin. It leads to inconsistencies.
Wow. We've spent the better part of a century looking for this theory of everything, and this proof is saying the final theory can't even be written down on a computer. It has to be something more, something non-algorithmic.
That is the profound implication, yes. The deepest layer of physical law seems to require a foundation that goes beyond what algorithms can capture. Reality transcends computation.
Okay, the math says impossible. But then the sources also bring in physicists who look at it from a different angle, right? More practical constraints.
Yes. Shifting gears a bit to information theory and thermodynamics. Work cited from physicists like Franco Vatsa, for example. Even if you somehow ignored the pure logic problems, the simulation idea runs into just massive physical roadblocks.
Resource limitations, basically.
On an unbelievable scale. Two main ones, memory and energy.
Okay, let's start with memory. The storage space needed.
To accurately simulate quantum phenomena, even in a small region of space, Things like the quantum Hall effect.
Yeah.
The amount of information you need to track, the memory required, it grows exponentially. It blows up incredibly fast.
Exponentially.
Yeah. The sources estimate that simulating just a tiny fraction of the observable universe perfectly, down to the quantum level, would require more bits of memory than the total number of atoms in the observable universe that could even theoretically sleep for information.
So, you literally couldn't build the computer inside the universe it's supposed to simulate. There isn't enough stuff to make the hard drive.
Pretty much. Yeah, it's physically impossible from a resource standpoint.
Okay, that's a big practical hurdle. But what about the energy? You mentioned energy.
Right. Even if, let's imagine, you had infinite memory somehow, you still face the energy problem. This ties into a fundamental principle called the Landauer limit.
Landauer limit. I think I've heard of that. It relates information to energy, right?
Exactly. It's a basic part of thermodynamics. It states that erasing a single bit of information in any computational process has a minimum energy cost. It must release a tiny amount of heat.
Okay. So running a calculation generates heat. We know that from our laptops.
Yes, but scale it up. Simulating the entire universe's evolution over billions of years. Think about the constant calculations, the updating of states, the erasing and rewriting of astronomical amounts of information, trillions upon trillions of bits every microsecond.
That's going to generate a lot of heat.
An impossible amount.
Yeah.
The calculations show that the heat generated by running the simulation would exceed the total energy equivalent of the mass within the universe itself. The simulation would basically cook itself, requiring more energy than the system being simulated contains.
You couldn't dissipate the waste heat fast enough? The simulation would be thermodynamically unsustainable.
It violates fundamental energy conservation principles. It's just too computationally expensive, too demanding in terms of raw energy to actually run.
Wow. So, logically impossible based on math, and practically impossible based on memory and energy constraints.
That's the two-pronged argument presented in the sources. It really seems to close the door quite firmly.
Okay, let's talk implications then, because this is big. One idea that always comes up with simulations is the recursive argument, simulations all the way down.
Ah, yes, the idea that maybe our simulators are themselves in a simulation, created by their simulators and so on, maybe infinitely.
Right. Does this proof address that possibility?
It seems to, directly. The core of the proof is that our universe is non-algorithmic. If that's true, then any hypothetical parent reality that could create ours must also possess non-algorithmic properties.
Because you can't simulate something non-algorithmic with a purely algorithmic system.
Precisely. So the chain breaks at the first link. If our reality isn't code, the reality that supposedly runs it can't be just code either. The whole idea of an infinite stack of computational simulations seems to collapse.
That really shifts the philosophical ground, doesn't it? If reality isn't fundamentally computational, what is it? The research mentions a Platonic foundation.
Yeah. That's a fascinating framing. It suggests that maybe the basis of reality isn't digital, like ones and zeros, but something more like pure information, abstract structures, maybe closer to Plato's idea of perfect timeless forms than to a computer program running in space-time.
So less matrix, more abstract mathematics is the bedrock.
Something like that. It suggests a reality that's fundamentally informational, but in a way that transcends algorithms.
The huge takeaway here, then it feels like, is that the simulation hypothesis, which lived for so long in this hazy space between philosophy and physics,
had potentially been moved into the category of scientifically falsified ideas, which is honestly incredibly rare for such a deep, almost metaphysical question.
It really is, and it forces a major rethink, doesn't it, about what physical laws even are.
Definitely. If the ultimate laws, the theory of everything, can't be purely computational, then the goal changes. Physicists aren't just looking for the code of the universe anymore.
They need something more.
Maybe a meta-theory, as the sources suggest, a framework that can incorporate these non-algorithmic truths, acknowledging that reality itself somehow goes beyond computation.
Okay, so let's try to summarize the core message here, the certainty that comes out of these sources for you, the listener.
The message seems clear. You are, provably, living in the original base-level reality.
Not a simulation.
Not a simulation, because the universe possesses a kind of irreducible complexity, a fundamental non-computability. Its deepest laws simply cannot be captured or encoded within any formal algorithmic system, no matter how advanced.
It's too rich, too complex, too. Mathematically awkward, maybe, to be software.
You could put it that way. And that leaves us with a final thought, something for you to really chew on. If these findings hold, they prove that reality is demonstrably more complex, maybe inherently more mysterious than any computer program could ever be. if the universe's own rules can't be fully contained within a logical, algorithmic system? What does that really say about our own human ability to ever achieve total knowledge? Complete prediction.
Hmm. It suggests limits.
It suggests there might always be an element of inherent surprise, maybe. Something about the universe that resists being perfectly pinned down by formal logic alone. Reality might just be fundamentally richer than our systems for describing it.